Hello everyone, welcome back all you. This has gone a long time to continue my hitherto lecture series. Sorry for that. Anyway, let's start the next topic of our ongoing series, matrix methods in geometrical optics. As I am remembering, the last lecture was about the translation matrix or refraction matrix. So in the continuation in the same series, let us now cover a new topic which is very most important to understand the upcoming lectures of matrix methods in geometrical optics. Whatever we will doing in this lecture, that will be that will be used in such lectures, like we can find the focal length of a metrical system or optical system in which a number of or a set of lenses or mirror will be given to us. On the other hand, this method is also useful for such kind of phenomena in which multiples objects as well as images are there, and we are willing to find the situation and the size shape of the formed image. Okay, so the lecture for this video is simply matrix system. By the word system, you can take a general idea that in this lecture I will be talking about such kind of system, and system comprise more than one or two things. Okay, so obviously in this lecture the more than one or two lenses or mirrors or optical medium will be there, and the image of a particular point object will be formed throughout that particular system, and we will be dealing about the matrix system of that particular whole the system. Okay, in the simple words, we will be having more than one lenses or mirror, and one object may be in the front of that particular lens or mirror, and the image of that particular object will be formed throughout whole the process or whole the system of lenses or optical systems, and we will be finding the image, distance, focal length of that particular whole system, or the other optical characteristics of that particular image or object. As in the continuation of the lectures in my lecture series, the matrix method will be used. Okay, so I will be creating such kind of matrix system in which the multiple lenses or mirrors will be using in order to create the image and hold together all the images formed by particular one mirror or lenses, and in the consequences other lens and then other lens will be there, and finally we will get a particular image. Okay, so let us draw a diagram to recapitulate this phenomena. Let us say this is a particular medium which is separating particular which is separating two medium. Let's say this is a medium on the left side of this lens, and the other medium is there on the right side of this lens. For the convenient, let us give the optical characteristics like refractive index to this medium. So for the convenient, I am regarding that mu I, this is I, is the refractive index of the left side medium. On the other hand, the right side medium had some different refractive index. Let's say this is mu1, right? Again, let's say there is another lens in front of this lens, like this, which is also separating this medium having refractive index mu1 to the another medium which may have different refractive index. Okay, let's say this is mu0, mu I, mu1 or mu0. So these are the three mediums what I am taking into the consideration. So this comprises a system of lens. There may be a multiple number of lenses or mirrors in this particular case, but for the convenience I am taking only the two. Whatever I will be doing about this two lens system, that will be the same procedure for the multiple lenses consecutively. Okay, so let's say this is the this is the principal axis. Let's say this is x dash x. Okay, and somewhere there is a point object from which a ray is coming from point A. Let's say from this is point A. So a ray is coming from this point and it strikes on this lens. Okay, let's say this point is B, and the point of the origin of this ray is A. After the reflection through this lens, this ray may go in this path, following this path, and again strikes at this boundary medium. Let's say this point is C, ABC, and again this undergoes another reflection in this way. Okay, so now we are having here one translation phenomena from A to B procedure, and at the point of this intermediate interface at point B, refraction is taking place. Again from B to C, this is a translation of the ray. Again when the ray strikes at point C, this undergoes a refraction. This is a second refraction. First refraction has been taken place at this point, and the other refraction is taking place at this point C. Again when it is refracted at this point C, it goes through the again a translation. Let's say this point is D here. Okay, for the convenient I am taking this particular distance as yi. Okay, so this is the height or distance. Okay, again I am taking this distance as, let's say, y1. Okay, and this distance or height is just let's say by 3. Okay, let me take this distance for the two situations. One for this on the left side, because at this point B, when the ray comes from point A and goes at point B, it is undergoing translation till now. Okay, so at point B, first translation is taking place, so this distance should be used for this translation phenomena. So this distance is y1 for the translation phenomena, and let's say this distance is y2 for the refraction phenomena at point B, and obviously that they will be same. So this y1 and y2 will be the same. Again I am repeating, y2 is the distance from the point B to this principal axis for the refraction phenomena, as well as y1 is the distance from the point B to the principal axis but for the translation phenomena. Okay, again let's say this distance is y3 for the translation from B to C at point C, and the refraction at point C to D, this distance is y4. So y3 and y4 again will be same in the magnitude or direction as well. So the direction of the ray is A to B, B to C, and C to D. Again let's say there is you can also regard this distance as y5 or y6 if you are interested to make this ray again multiple reflection or refraction. Okay, so let's say this angle is nothing, alpha I. Okay, and this angle is again will be alpha I. Okay, and this angle, let's say this becomes alpha 1 here, this is alpha 1. Let's say this angle is alpha 2 here, and this angle is alpha 3 here. Okay, So combinedly, as you know very well, y1 and alpha 1 are simply, or y or alpha are simply known as the coordinates of the paraxial ray. Okay, so distance and angle are the coordinate for the paraxial ray. So the coordinate for this phenomena A are y1 and alpha 1, yi and alpha I, and at point B the coordinate for the same ray are y1 and alpha I. Okay, and at point B for the refraction the coordinate are y2 and alpha 1, right? Again, for this translation at point C till from B to C, the coordinates are y3 and alpha 2, and for the refraction the coordinates are y4 and alpha 3. Also, you have some idea about the matrix generation for the translation or refraction procedure. As in the last videos, I have covered to how we can find the matrix for the different reflection or refraction procedures. So any reflection or refraction, the matrix is nothing as the output coordinates. Let's say output coordinates are y or alpha. This is the matrix for output ray, and whatever the refraction or reflection taking place, that notation is here, or this is the reflection or refraction matrix. The element may be there, and this is the input matrix. Again, let's say this is yi and alpha I. So this is some basic structure to create a matrix, what we have studied in the last lectures. So I am going to do the same. I am going to define the different matrices for the all the, how many phenomena these are? These are 1, 2, 3, 4 and 5. Here 2 phenomena will be taken, because one for translation and therefore refraction. Again, one for translation and therefore refraction. Okay, so sorry, translation, this is refraction, and again translation. So let us apply the matrix method for this translation from at point A, okay, and point B. So for translation from A to B, matrix will be like this. Output matrix should be written in the first form. So this is the output matrix for this translation. Translation is ending at this point B, which is originating from point A. Okay, so translation is only taking place from A to B and ending at point B, again because refraction is taking place at the another time. Okay, so at this point the refraction coordinates for the translation matrix will be like output matrix. So they will be y1 and this is alpha I. This is y1 and alpha I. Sorry, alpha 1. Okay, so these are the output coordinate matrix, right? Now here translation is taking place, that's why I am writing it as translation 1, translation matrix 1, and it will be multiplied with the input matrix, from where the rays input at this point A. So at the point A, the coordinate for the paraxial ray are yi and alpha I. So this is for this procedure from A to B. Now the refraction at point B, what about for refraction at point B? For refraction at point B, so the output coordinate for the refraction at point B will be y2 and alpha 1. Okay, y2 and alpha 1. So they will be y2 and alpha 1, and here this is y1 and alpha I will be taken, because translation is ending at point B, and at the left side y1 and alpha I are the coordinates. Sorry for this. So at the refraction, the output coordinates of the paraxial ray are y2 and alpha 1 this is. And from where this ray is coming into for the reflection? From the y1 and alpha I. So they will be input coordinate. And which phenomena is taking place at this point P? Point B, refraction is taking place. So that will be refraction matrix, and this is a one refraction till now. This is refraction matrix 1 into the input matrix coordinate. So that these are y1 and alpha I. y1 and alpha I, because input ray is coming from this. So this is equation 2. Now again the ray, translating ray B and C is going in such a way that translation is taking place. So from point B to C the ray is translating into this medium, right? So again for translation from B to C, this is B to C. Again I should take the output coordinates. So these are y3 and alpha 2. Okay, so these are y3 and alpha 2. Okay, and here translation is taking place, and this is up till now second translation, because first translation is already happened at this point B, up till point B. So this is the second translation at this point C. So this is translation matrix, but second, because one translation has been taken place at this point. Now multiply with the input matrix. So input matrix will be consisting of y2 and alpha 1 as the coordinate. So these are y2 and alpha 1 as the coordinate. Let's say this equation is 3. Now I will be repeating the procedure. Again at point C, refraction is taking place. When the ray BC goes into this lens or this system of the optical system, refraction is taking place. So for the refraction, at point C. So at point C, what are the output coordinate of the paraxial ray? Output coordinates are alpha 3 and y4. Okay, and the input coordinates are y3 and alpha 2. So output coordinates are y4 and alpha 3. This is the output matrix, equal to the which phenomena is taking place? Refraction is taking place at this point, right? So I am writing here the refraction, and this is second refraction, because first refraction is already have taken place at this point. And should we multiply with the input matrix? So input matrix is y3 and alpha 2. This is going to as equation number 4. Okay, so this is how I have generated this complete, I have recapitulated the complete phenomena according to their respective matrices. So from where we have started, I have started at this point A, and now I have reached at the point C. At point A, ray was coming from point A to B in the translation. At point B, it has undergone refraction. From point B to C, it has undergone translation. At point C, it is also going to the refraction, and finally from C to D, it is going to translation. Okay, so I have to write also this translation matrix again. So let's say this distance is by 5, and this angle is, let's say this is alpha 3, because these are the alternate interior angles. So for translation from C to D, again, so final output matrix coordinate are by 5 and alpha 3 equals to translation is taking place. So this is third translation up till now. First translation, second translation, this is third translation is going on, and the input coordinates are by 4 and alpha 3. By 4 and alpha 3. Right, this is equation number 5. So you can see only taking two lenses, 5 phenomena are here. Okay, one phenomena is here, second, third, fourth and fifth. So only taking two lenses, 5 phenomena are happening. What will happen if I am taking the, let's say, 5 lenses or 5 mirrors? That will be a large number of the matrix. But after recapitulating all these matrices, we can concise the complete phenomena only in terms of 2 matrices. How? Let us now do that. So I am removing this diagram. Now in term the equation number 5 can be written as in terms of its preceding matrices. Okay, so equation 5 can be written as, equation 5 can be written as, here by 5 and alpha 3 is here, this is by 5 and alpha 3. Okay, and this is going to equal as what? Translation matrix 3. This is translation matrix 3. Okay, multiplied with the by 4 and alpha 3. Okay, now what is the value of by 4 and alpha 3? Means that this input matrix for this output matrix, so y 4 and alpha 3, this complete matrix is going to equal as Rm2 and y 3 and alpha 2, this complete equation 4. So I can just replace y 4 and alpha 3 matrix with this equation number 4. So this is nothing but refraction matrix second and multiply with the y 3 and alpha 2. Okay, so I have just jump from the equation 5 to 4. Again, now here I have by 3 and alpha 2. What is the value of by 3 and alpha 2? This complete matrix. By 3 and alpha 2 from here can be written as its RHS part. Okay, so more interestingly, this equation can be lead as multiply the by 3 and alpha 2. By 3 and alpha 2 is nothing but translation matrix 2 multiply the what? Y2, and this is alpha 1. Again, this y2 and alpha 1 can be exchanged by this complete equation. Y2 and alpha 1 is y2 alpha 1 is equals to Rm multiply Rm1 and what? This is y1 and alpha I. Okay. Again, follow the same procedure. Y1 and alpha I just equals to Tm1 and by I alpha I. So this is multiplied with what? This is Tm1 and this is yi and alpha I. So this is the concise form of the equation number 5. Means that this is the actual output matrix. Okay, so I am just removing this diagram, so this complete interpretation, and just redrawing the diagram. So the diagram was, this was mu I, this is mu 1 and this was mu 2, sorry, mu 0. And here you can see for this left side y1 and by I and alpha I were taken. At this point y1 and alpha I is taken, and this point what? Y4 and alpha 3 were taken, and for this translation, final translation, y5 and alpha 3 were taken. So y5 and alpha 3 were the actual output matrices for the last translation. which is here by 5 and alpha 3, and from where I have started this complete mathematical interpretation or this phenomena, from where this phenomena was starting. This was starting from this point A, whose coordinates were y, I and alpha I. So these are actual input coordinates, okay, and these are here y and alpha I. It means that this is the initial input matrix. So I can write this input matrix as this one, input matrix, and this is what? This is the actual output matrix. Now what is the relation between the output matrix? This is this complete multiplication and multiply by this input matrix. Let's say this complete multiplication of different kinds of matrices is Sm. And what is Sm here? So Sm here is the system matrix. So Sm is just what? This is translation matrix 3 multiplied the refraction matrix second, and translation matrix second multiplied refraction matrix first and translation matrix 1. So this is going to as system matrix. So this complete system matrix is just replaced by a one matrix which is simple known as system matrix. So the product of the different or multiple matrices which were coming from the different or multiple phenomena of reflection or refraction can be concised as one system of matrix, which is simply known as system matrix. Why we use this? We have gone through this complete phenomena, right? In this complete phenomena, there were multiple reflections were taking place. Okay, in order to get rid of the complexity or cumbersome of this process, we can take this complete system matrix for the old multiple different translation or reflection matrix. So how many there were the reflection or translation taking place? You can just concise all the reflections and translation in one matrix which comprises that particular system which was taking place in the optical phenomenon as Sm. So Sm is nothing but the, just remember, this is the reverse multiply or reverse product. Here Tm3 is taken, multiply Rm2, and again that was Tm2, Rm1, Tm1 is taking place. Okay, do not forget to write this complete matrix system without order. Okay, so you have to remember, you should check, you should be disciplined according to writing this. What I can say like this, it's the order. Okay, so first the last matrix should be at the first place, and then second last method should be at second place, and the third last matrix should be at the thirding and the succeeding terms. Okay, so do not write the following. You cannot write this Tm1 multiply by R1 multiply Tm2 multiply Rm2 and this is Tm3. No, that will be wrong. Okay, so here as M is simply known as system matrix. How we will use this system matrix in our actual life or actual life phenomena? So let us see that particular application of the system matrix in the upcoming video lectures. Okay, so thanks for watching. Let's meet in the next lecture by taking some such kind of scenarios in which we will be finding the focal length or mirror formula or lens maker formula by using the system matrix like this mathematical interpretation. Okay.